on the previous page, we had determined that so let's see, what was the function? The function was f of x equals 2x cubed plus 3x squared minus 12x plus 4. And before we had determined that the critical points are x equal -2 and x equal +1. Now, if we look at the interval that we're given on this problem, it's from 0 to 2. So the critical point, x equal -2, is not in the interval. So in fact, we don't need to consider it in this case. So what we need to do is we're going to use the extreme value theorem, which the extreme value theorem says that if you have a continuous function, which we do have a continuous function on a closed interval, that the extreme values will occur either at the endpoints or at the critical points. And so we can look at the function evaluated at the endpoint 0, and also evaluated at the critical point x equal 1, and at the endpoint at x equal 2. So this is a critical point, this is an endpoint, this is an endpoint. And then we threw out the critical point x equal -2 because it's not contained in the interval. So we don't need to consider what that is. So basically we just want to take these values and plug it into our original function f. So if we plug 0 in there, we'll get 0 plus 0 minus 0 plus 4. If we plug 1 into there, we'll have 2 plus 3 minus 12 plus 4, which is equal to, let's see, 4, 5, 6, 7, 8, 9, -3. And then f of 2, well, I'll have 2 times 8, which is 16, plus 3 times 4, which is 12, minus 12. Minus 12 times 2, which is 24. And then plus 4. Okay, so what does that give me? 16, 20, 32 minus 24. So we get 8. All right, so the biggest one of these is the maximum. And the smallest of these is the minimum. For the next one, I want to build a rectangular storage area consisting of 3 separate compartments. The fencing costs $2 per linear foot, and my budget is $160. So if it costs $2 a linear foot and my budget is $160, I know that the total amount of fencing is 160 divided by 2, which is 80 feet of fencing is what I can do here. And if I look at my fencing, I notice that I have 2 of these lengths, and then I'll have 4 of these widths. And if I add that all up, that should equal the total amount of fencing. So, so we'll write that down. Okay, and what is it that I'm wanting to do here? What's my goal? My goal is I want to maximize the total area. So what that means is that I need a function that gives me the total area. So the area, and then this here, this is my constraint. The area of this is basically just a rectangle, so the area of this is the length times the width. And so I can use this function here to solve for one of my variables. So I can solve that for L, say, and I'm going to get 2L equals 80 minus 4W, so L is equal to 40 minus 2W. So then I can replace that in here for L. And the reason is now I have an area function as a function of one variable. So So my area function, a of w is equal to 40w minus 2w squared. So if I want to maximize that area, I want to find the maximum of this function. So our goal is to find the max of this function. So that's our goal. So to find the maximum of that function, first I'll take the derivative and set it equal to 0 to find any critical points. So if I take the derivative, I get 40 minus 4w, and if I set that equal to 0, I get that the width is 10. And if the width is 10, I can use this equation over here to find the length. So now I have the width and length of this rectangle that I'm trying to find. How can I be sure that that critical point actually gives me a maximum? Well, what I can do is I can look at the second derivative. What is a double prime? A double prime of w is -4. So what that means is that my function at that maximum is concave down at that critical point. So that means it is a maximum. And that's what we were looking for, because we wanted to maximize the total area, not minimize. So those are our dimensions, length and width. So for the next one, I'm given a flow rate at which an oil well is leaking out in barrels per hour. And so I'm given a table here. I don't have a function for my flow rate, but I am given a table. So I ought to be able to use that table to compute some things. So let's see. So I want to do a left endpoint approximation with 4 subintervals to approximate the volume spilled over the entire 24 hours. So this is the time period that I want, and I want to divide that into 4 equal pieces. So I'm going to start by, let's divide it in half, and then divide the halves in half and kind of see that. Now what I want to do is a left-hand approximation. So I'm going to take my readings here from the left-hand side of each of these intervals. So the first interval will be, I'm computing the rate, I'm using the rate of 81 over the time interval, the time interval is 6-hour time period. And then for the next 6-hour time period, I'm going to use this reading here, 49, for the next 6-hour interval. Then I'm using this measurement of 25 for the next 6-hour time interval. And then for the last 6-hour time interval, I'm going to use this reading of 9. And if I compute all of that, I'm just going to plug it into my calculator. Okay, if I just plug that all into my calculator, I'm getting 984. Now, what will be the units of this? Well, let's think about what it is we're multiplying here. So this 81 here, this is a rate. And the units of that are barrels per hour. And then what is this 6? Well, that's the length of my time period. And what is time measured in? It's measured in hours. So if I multiply each of these things here is a barrels per hour times hours, then the output should be just barrels. So then it asks, is my approximation an underestimate or an overestimate? Well, if I think about it, during the first 6 hours, my flow rate is decreasing. So I start out at the very beginning with a flow rate of 81 barrels per hour, but by the end of that 6-hour time period, my flow rate has decreased down to 49. So if I use 81 as my flow rate for the entire 6-hour time period, that would be an overestimate. So this is an overestimate. And the reason is because the rate of the flow rate, let's say the flow rate, is decreasing. And we were using a left-hand sum. So in other words, we're always using as our approximation for each of those time periods, I'm using an upper estimate for the flow rate for each of those intervals. Then I want to write an integral that represents the exact amount of oil spilled during the 24-hour period. So one thing we want to notice is that I don't have a construction for RT. I don't have to come up with some sort of function or anything. Don't waste your time doing that. I'm just going to use R of t. So what I want to do is I want to take that R of t and I want to integrate that thing from 0 to 24 hours with respect to time. So that's it. That's what it wants me to write right there.